Welcome to ADS University. My name is Will Humber, and in this lesson, we'll cover how to prepare and execute a conjugate heat transfer simulation using ADS code LEO via the workbench. We'll begin this lesson by covering the overall workflow process for conjugate heat transfer, learn about the sample case that we'll be using, go over a demonstration of how to prepare and execute a case using the workbench, cover some helpful tips, and finally, summarize what we've learned. The overall workflow occurs in 3 steps: mesh conversion, execution, and post-processing. In this lesson, we'll be covering mesh conversion and execution with the workbench, which will help with creating the setup files and executing the various tools. In the first step, we take an externally generated mesh, such as a CFX5 file from ISIM, and run it through our conversion tool, Geo, to produce a restart file. In the next step, execution, we have the option to break the restart file into multiple partitions to improve turnaround time. The restart files are then run through LEO until a converged solution is reached. In the third step, post-processing, we examine the solution using a post-processor such as TechPlot or ParaView. The sample case used for this tutorial series is a rectangular plate with a single film hole. The material used for the plate is Inconel 718. The core flow moves from left to right over the plate, while the cooling flow comes from a plenum below the plate. The solid contains 3 boundary conditions: hub adiabatic, represented by number 7, which will form an adiabatic wall, along with blade and vents, represented by 1 and 8 respectively. These will form fluid-solid boundary interface conditions, as indicated by the subscripts behind their names in the CFX5 list to the right. Moving to the fluid side, we've listed the boundaries in a similar manner, although boundary condition 2 in this case is hidden from view due to the nature of the geometry. This boundary condition table, which we will construct later on, will be used to associate the boundary names from the CFX5 file with internal boundary condition types from LEO. From the workbench, our first step is to create a new CHT case. Next, we need to give the case a name and associate it with a project. Once this has been done, we can select the CFX5 file containing our mesh. The workbench will now read the CFX5 file and extract the mesh information and boundary names. This next screen is used to set the initial boundary conditions for the simulation. Beginning from the top of the general section, we have the CFX mesh coordinate system. In this case, it will be Cartesian. The units of the incoming system, in this case, English units. The wall type. This sets the boundary condition on the CHT interface walls. In this case, we want wall functions. The direction of the flow for the initialization. For this case, we'll choose axial. Followed by the rotational speed, the ratio of specific heats, the downstream static pressure, and the initial wall temperature. At the inlet, we must specify an initial guess for the inlet Mach number, followed by the total pressure and temperature, along with the flow angles and the axial or radial location of the inlet. The last section of this screen is used for specifying the initial conditions of the outlet. Here, we only need to specify the flow angles and the axial or radial location of the outlet. Moving on to the next screen, we can set the initial temperature for the metal and the metal material properties. A list of 9 commonly used alloys is included, but the option to use custom specified properties is also available by selecting the custom option. And then pointing to a custom material property file. In this case, we'll be using Inconel 718. The next screen contains a list of optional parameters. The first parameter allows the user to convert a Cartesian input mesh into cylindrical coordinates. The second parameter is used to swap axes definitions. And finally, the third parameter is used to scale the mesh by some real number. Next up is the screen for setting the boundary condition types and values. These are the same boundary conditions that were previously mentioned when describing the sample case. To begin with, we'll change vents 1, vents 2, blade 1, and blade 2 to wall function CHT type boundary conditions. These boundaries represent the fluid-solid interface. Next, we'll set the inlet conditions by changing the boundary inflow to an inflow type, which results in the following dialog appearing. You can choose either unit vectors or flow angles to specify the flow direction, followed by the inlet Mach flow number, total pressure, total temperature, and the unit direction vector of the incoming flow. Similarly, when choosing an outflow condition, the following dialog appears. In this case, we can choose the static pressure at the ID, along with the radius at the ID, the static pressure at the OD, and the radius at the OD. Next, we'll set inflow shroud to an inviscid wall, inflow hub to an inviscid wall, hub adiabatic to an adiabatic wall, and finally hub inflow to another inflow condition. We'll set the inlet Mach number, inlet total pressure, inlet total temperature, and finally the flow direction. Looking at the inflow and hub inflow conditions, we can see that inflow is named 00 inflow and hub inflow is 01 inflow. The 2 digits in front of the boundary condition type name are used to identify and separate out unique boundary conditions of the same type. On this screen, we can set the settings for partitioning the mesh using ADS-util. The first parameter allows us to tell ADS-util if the fluid-solid interface is a wall function or wall integration type boundary. The second parameter tells ADS-util how many pieces should be broken up. And the third parameter tells ADS-util how the mesh should be broken up. The final screen allows us to modify the Leo solver settings. In this case, we'll use all of the default settings except we'll change the number of iterations from 6,000 to 5. For more information on Leo settings, see the Configuring a 3D Steady Simulation with the ADS Workbench tutorial. Now that all the setup files have been completed, we can convert the CFX5 file to a restart format using the command here. The first step for Geo is to convert the fluid followed by converting the solid. Once Geo has converted the CFX5 file to restart format, we can either run the case in serial or break up the mesh and run the case. To break up the mesh and run the case, click the Break Up Fluid Mesh command. In this case, we're breaking the mesh up into 3 pieces and then running for 5 iterations. Now that the CHT simulation has been finished, we can open up the folder and begin looking through the results to start the post-processing. One issue to watch for is when setting the initialization bounds, make certain they are accurate, as inaccurate values can cause a poor initial flow field. When running CHT, it is critical to separate fluid-solid interface walls from non-interface walls. Failing to do so can cause Leo either to crash or give poor results. Additionally, if something seems off with the conversion, always check the geodebug.data file. In this lesson, we learned that the ADS Workbench can be used to facilitate the setup and execution of conjugate heat transfer simulations. The Workbench can help with CFX5 mesh conversion, specification of material properties, setting up boundary condition types and values, partitioning the mesh for improved performance, and execution of the simulation. We highly recommend the Workbench as a learning tool for the conjugate heat transfer process, for both beginners and experienced users alike. While mesh conversion and execution can be performed with the Workbench, post-processing should still be done with an external tool, such as PowerView or TechPlot. For more information on CHT, or to download the sample case, please visit the ADS support portal at adscfd.com. Thank you, and goodbye.